Every single diagnostic ultrasound image we look at is actually a continuous physical negotiation of high-frequency sound waves. We can map the clarity of the resulting image along three specific dimensions: the axial, the lateral, and the temporal. Measured, precise. These physical properties exist in a strict zero-sum environment. Optimizing the values along one axis mathematically forces a degradation along another. Modern ultrasound machines deploy nonlinear wave propagation and complex geometry to partially bypass these foundational limits. To yield a precise clinical diagnosis, an operator must understand the physical equations governing the sound waves, actively manipulating the image to isolate specific targets. This diagram illustrates axial resolution along the z-axis, the ability to differentiate objects along the ultrasound beam's path. Distinguishing these dots depends on the pulse length. A short pulse generates distinct echoes from each target. A longer pulse overlaps them, blurring into a single entity. Achieving that necessary short pulse requires two specific hardware conditions: a high-frequency wave and backing material inside the transducer with a low Q value to physically dampen the crystal's vibration. Shifting to the x-axis, lateral resolution distinguishes side-by-side objects. It's governed by an equation: beam width equals focal length times wavelength divided by d. d is the probe's crystal diameter. As diameter increases, wave interference dynamically constructs a narrower, higher-resolution beam at the focal point. Because of these differing mechanics, lateral resolution is inherently inferior to axial resolution. As a general clinical rule, the lateral resolution typically equates to roughly 1/3 of the transducer's physical diameter. The third spatial dimension is the slice thickness, or elevation resolution. For standard 2D transducers, this structural thickness is fixed. The slice thickness scales inversely with the beam's frequency. You can only minimize it by utilizing a higher frequency transducer. Spatial resolution is strictly dictated by probe hardware geometry and sound wavelength, establishing a hard limit on the minimum size of detectable pathology. Moving to the dimension of time, we arrive at temporal resolution, represented as the system's frame rate. The absolute ceiling for this frame rate is unchangeable. It is the physical speed of sound traveling through human tissue. This timing is the pulse repetition frequency, or PRF, the rate of pulses transmitted per second. The machine operates on a strict wait time rule. It cannot transmit a new pulse until it receives the previous echo. Scanning deeper targets increases the round-trip distance, forcing the PRF to drop. Widening the sector width forces the machine to fire across more space, requiring more time per frame. Adding focal zones introduces a heavy cost. Each zone requires an entirely separate sound pulse down every scan line. Activating Doppler mode requires significantly more pulses per scan line to calculate blood flow velocity, penalizing frame rate. First is depth, then sector width, next focal zones, and finally Doppler. Each variable acts as a cumulative tax on the machine's speed. Temporal resolution is simply the absolute time cost of scanning. Larger, deeper, and more complex views physically force a slower, degraded image. When scanning deep tissue, standard high-frequency fundamental waves fail. They attenuate quickly, losing their energy before reaching the target. To bypass this without sacrificing spatial detail, operators use harmonics, a method that exploits the nonlinear physics of high-intensity sound in human tissue. The core mechanism relies on nonlinear propagation. As an intense sound wave travels, its high-pressure compression phase travels faster than its low-pressure rarefaction phase. The wave deforms as it moves deeper, steepening the leading edge of the sinusoidal wave. This continuous physical distortion generates entirely new, higher-frequency harmonic waves directly within the deep tissue. On this frequency spectrum graph, Fourier analysis isolates returning harmonic multiples. The machine uses an electronic filter to completely discard the fundamental frequency, rendering the image strictly from the tissue-generated harmonics. This creates a distinct physical advantage. Because these harmonic frequencies are generated at depth, they only travel a one-way path back to the probe. In standard imaging, the outgoing high-energy beam bounces between the skin and the probe face, creating near-field clutter known as reverberation. But since these harmonic waves aren't formed until the sound is already deep in the tissue, those superficial bounces are never captured. This reduction in clutter is essential for specific scenarios: cardiac imaging through ribs, assessing fluid-filled structures, scanning obese patients, and measuring carotid artery walls. There are physical limitations to this technique. Harmonic generation relies entirely on acoustic intensity, meaning the effect dissipates and is lost at extreme depths. Furthermore, generating that required nonlinear distortion demands high-power ultrasound outputs from the machine, which must be managed for patient safety. By exploiting wave deformation, harmonic imaging turns the patient's own deep tissue into a secondary transmitter, trading raw power for artifact-free clarity at depth. Another specific failure point in spatial resolution occurs when highly reflective or attenuating structures create dense acoustic shadowing, obscuring vital tissues behind them. To bypass these blind spots, the system can utilize spatial compound imaging, a geometric solution to an acoustic problem. The mechanism relies on beam steering. The transducer electronically fires pulses at up to 9 intersecting angles per sweep. These highly angled beams physically reach behind the obscuring object, returning echoes from previously hidden regions and dissolving the acoustic shadow. This technique is optimal when examining superficial structures and small parts, where achieving wide intersecting acoustic angles is geometrically possible. However, this spatial gain carries a high temporal trade-off. Firing up to 9 separate pulses per scan line forces the machine to wait 9 times longer to complete a sweep, resulting in a significantly lower frame rate. Spatial compound imaging restores hidden spatial data, but strictly at the cost of temporal resolution and acoustic shadows, which themselves can be useful diagnostic artifacts. Looking at this interface of physical constraints, we can pull all of these variables into a single interconnected model. Ultrasound physics is a zero-sum game. You cannot mathematically increase spatial clarity without paying a temporal or power penalty. Axial and lateral limits remain strictly geometric problems, bound by the physical hardware of the transducer crystals and the fixed wavelength of sound. Harmonics and compound imaging exist as advanced computational workarounds, exploiting nonlinear physics and beam steering to erase specific artifacts from the field of view. True clinical mastery requires understanding the mathematical equations of the beam to deliberately choose exactly which physical limit to sacrifice for the sake of the diagnosis.